Hi, this is Mrs. Jackson. This is Chapter 3, Section 5, Part 2. And in this quick little video, we're going to look at the derivation of the binomial theorem and actually what the theorem looks like. Side note, you can look at some of this work on page 149, example 4 in your textbook. And it's probably a little bit of an overstatement to say that this is a derivation of the theorem. We're really just going to look at one particular example and observe how that looks compared to Pascal's triangle, and then really look at the theorem. So it serves as a little bit of a proof anyway. Okay, let's get started. So let's take a look at a binomial, x plus y, raised to the power of 4, and see what that looks like. So we know that we could rewrite this as x plus y squared times x plus y squared. We still have 4 x plus y binomials being multiplied together. I broke that out only because we've already looked at the square of a sum. We know x plus y squared is x squared plus twice their product, or 2xy, plus y squared. So that's 1, and that's being multiplied by the same thing itself. So they are equal. So our task here is to multiply 2 identical trinomials together. That's a lot of terms, kind of messy. So I'm going to organize my work with the box method here. So I'm going to very carefully draw a box. I've got 3 terms multiplying 3 terms. So I'm going to make a box that's 3 by 3 just to organize all my distribution. So on one side here we have x squared, 2xy, y squared, and over here we have the same, x squared, 2xy, y squared. The box method again is not necessary, but it does help. So if we start our distribution, x squared times x squared gives us x to the 4th. And likewise, y squared times y squared gives us y to the 4th. I'm going to change colors here. If I have x squared times 2xy, that is going to give me 2x cubed y. And likewise here, if I have x squared times this 2xy, we're going to end up with the same thing, right? 2x cubed y. And if we move over some columns here, I've got x squared times y squared. I'm going to change colors again just to help illustrate the different terms. This is going to give me x squared y squared. And 2xy times 2xy is going to give me 4x squared y squared. And y squared times x squared is going to give me x squared y squared. And I'm going to change colors again. Moving over here, I've got 2xy times y squared is going to give me 2x y cubed. And y squared times 2xy is going to give me 2x y cubed. So we can see our like terms always when we use the box method. You're going to see your like terms on the diagonals. So we've got these like terms we could combine, and these like terms we could combine. So let's start writing down what we have as a result. Maybe I'm going to put this in a different color. I'll put it in black. So this first term here, x to the 4th. And I have the sum of 2x cubed y plus 2x cubed y is a total of, you know what, I'll keep these colors going, 4x cubed y. And then we have our green terms here. We've got 1x squared y squared plus another 1x squared y squared plus 4x squared y squared for a total of 6x squared y squared. Moving over to the other color here, purple, we've got 2x y cubed plus 2x y cubed is 4x y cubed. And finally, we have our last one here, y to the 4th. So this is the result of taking x plus y to the power of 4. These are our resulting terms. It's a polynomial. And if you recall in a previous video, I talked about how to write that in standard form when you have two variables. Some possible area of confusion here. We are not going to write this in standard form. So what we're going to do is we are going to have our x term, that's this first term. It might not be a variable, it might be a number, but that first term is going to be going here with descending order of exponents. If you notice, we've got x to the 4th. That's our biggest power here. X to the 4th, x cubed, x squared, x to the 1, and then there's no x. Really, it's x to the 0. And then as we step up, notice the second term here, y, is an increasing order of exponents. So we have no y, or y to the 0 power here, y to the 1, y squared, y cubed, y to the 4th. So as the first term is descending, the second term is ascending. So that's the order we're going to put these terms in. Now, let's take a moment and just recreate Pascal's triangle for 4 rows. Remember, the first row begins at 0. So we start out at 1, and then we have 1, 1, and then we have 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So if you look at our numbering here, this is row 0, row 1, row 2, row 3, row 4. In our example, our power is 4, n equal 4. So we want to look at the 4th row of Pascal's triangle, and what do you see? We see the numbers 1, 4, 6, 4, 1. I'll change colors again. We have an invisible coefficient of 1 here. Then we have 4. Then we have 6. Then we have 4. And then we have 1. So the numbers here that are in Pascal's triangle in the exact order is going to give us the coefficients that we need for our binomial expansion. So this is kind of amazing. It seems and feels a little bit like magic, but this is so awesome of a time saver. If you were to do binomial expansion, can you imagine doing a power of 7, 8, 9, or even bigger? It's pretty easy to make that Pascal's triangle very quickly. So much easier than doing out all of this multiplication and making sure you're getting all of these exponents straight. So this is quite a time saver. Now, I'm going to write down the resulting theorem here. It looks really a lot of subscripts and exponent superscripts. So it looks kind of messy and hard to understand, but it really isn't. So just kind of take it one step at a time here. I'm going to change back to blue. So if we have a sum here, a binomial, and we raise it to a power of n, the way that's going to look is we're going to have a coefficient. I'm going to use, well, I have it below here, coefficients, okay? C for coefficient. So we're going to start out with that very first term. I'm going to call it C sub 0, the coefficient. That's going to be the coefficient of a raised to the n. So that's my first term raised to that power. And then I'm going to add to it the second, well, we'll call it c sub 1, the next coefficient. Now I'm going to step down that a to the n. So if I want to step that down 1, that's going to be a to the n minus 1. And I'm going to step up b. So b to the 1 shows up. The next term, c sub 2, I'm going to step down that a exponent further. So that'll be n minus 2. And I'm going to step up b's exponent. So it was 0 first. Now it's b to the 1. Now we're going to say b to the second. And I'm going to keep going, dot, 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 with this pattern until I get to the second to the last term, which we'll call c to the n minus 1. And on that term, a is going to be up to a power of 1. And b is going to be up to n minus 1. And then the very last term, I need to move over here a little bit. The very last term is finally going to be c to the n, whatever that power is. Now that a term is gone. Okay, the second last term, it was a to the 1. Now we don't have a anymore. And the very last term is going to have b to the n. So what we have here is that first term in our sum here, a, has got descending order of exponents. Okay, I hit the last one. The biggest one going down 1, 1, 1, and then here it's second last term is to the 1, and then it's gone in the last term. And then the second term here, there is none. Here it's b to the 0, or just the number 1. And now it's stepping up b to the 1, b to the 2, b to the 3. Finally, b to the second to the last, so n minus 1, and then b to the n. So this is the binomial theorem, and we can pull those coefficients, c sub 0 up to c sub n, straight off Pascal's triangle. And those coefficients here, as we say, these coefficients are coming off the triangle, and you'd be pulling those off of row n. So whatever that exponent is, that's the row you're going to go off of on the Pascal's triangle. And it's important to note that the powers of that first term a, that very first term a, they are decreasing. They start at n, the largest, and they step down one increment at a time. And the powers of b, that second term in the sum, are increasing by 1 in each subsequent term. All right, so the last thing I want to say before I end this video is do note that a and b are just variable placeholders. They could be numbers, and often are numbers. So sometimes, you're not going to see these variables here, two variables. Often in case one of those will be a number, and you're going to be taking that number to a power and simplifying it. We'll get a chance to look at that in the next video and some examples. I hope this helps. Thanks for listening.